and now we are continuing with Ivano, the second part on string physics.
Very good. Thank you so much. Okay, so here is it good for Zoom if the whiteboard is or like up there? Okay, so I can leave it for now. Oh shoot! It's like the most important thing. Like what is happening? Like right, it's gravity. Like this is why I do. Well, ooh, burn. Uh, oops, it's too self-consistent to be burned. Anyway, so yeah, I pre-wrote a couple things here. So they're separated left and right halves almost of the not blackboard. So here there is a plan for today, right? So the plan is to take the construction of the theory that I gave you yesterday and look at the physical consequences, right? So I really want to sound like one of those, old wise professors, emeritus professors, like, what is physics, right? So physics is basically, at least here for what I care about here, states and dynamics, right? So I give you the theory. What are the states of the theory, and what does the theory actually do, right? Or you could say states and observables if you like. And then so we're gonna start by talking about the states, and then we're gonna talk about what the states do. Now the states can be of different kinds. Yes.
The next this lecture, you're gonna just focus on the worksheet action that does not contain the extra stuff that we introduced in another dimension.
That's right. That's right. That's right. I am going to try to mention some options for that. Yes.
Just as a curiosity, like let's suppose you want to add something and try to get some d equal to 4. Would you still manage to add something that respects renormalisability? That was the criteria that you used to justify the words.
You can, but you don't need to, because so you want, so again, and this is also not necessary for string theory in general, but if we care about a nice weakly curved tame, as I said, space-time, then the space-time piece needs to be weakly coupled, and therefore for UV completion perturbatively renormalizable. Now the rest just needs to be a conformal field theory or super conformal field theory, and you don't need renormalizability in any meaningful way, in the sense that the theory is conformal, like it's completely fine, and it need not be weakly coupled. Could be anything.
Because remember you said if we ask for renormalizability, these are the terms that we write down.
Yes, but I wanted that purely for the sake of obtaining a weakly curved spacetime in the end, right? Because this is the world sheet physics, right? Like the two-dimensional theory we're talking about. The space-time physics is something else, and it's actually what I'm gonna talk about today. Right? Yeah.
So the space works like a but let me say at the university form to this.
Of course, of course. Yeah.
How does that connect with the requirement of a weekly couple?
Then it won't be. Like you can the generalized version of the statements is just that the CFT needs to be, well, it needs to be C, it needs to be conformal, and then it needs to be critical and modular invariant. That's all. And this can handle, this definition, this description handles weak coupling, but arbitrarily high curvatures. So that's something that people do, people in ETH Zurich, for example, they study highly curved string backgrounds, for example. Alrighty, but of course you can also look at some strongly coupled description as well. Yeah. Yes, it's the coupling of the two-dimensional theory on the worksheet. And then there's the coupling of the actual strings in space-time. You see, that's the difference. We're gonna get to that. All right, cool. So yes.
dimensional theory.
Yes,
But it's not as target space theory.
absolutely. Okay, very good, very good. So the idea is that, you know, the spectrum of this worldsheet theory after gauge remember, the worldsheet is not merely a two-dimensional conformal super conformal field theory, it's coupled to gravity or supergravity on the worldsheet, which makes the space-time picture possible. And therefore the spectrum of the theory will be slightly different, right? Because it has to be consistent with gauge redundancy. And this is very, very important. And it will turn out that, you know, the spectrum of these strings, and remember, this is a single string spectrum. Then in space-time, you can have, you know, multiple strings interacting and so on. The single string spectrum has certain masses. And you can have very light states relative to the EFT cutoff, precisely massless states, for example. And stuff that is new physics that you cannot see in the effective field theory. And this is where I will try to do like first hour and a half and second hour and a half. So infrared physics and UV physics. Does that work? Yep. So this is a recap of what we did yesterday. So we started from general considerations of gravitational EFTs. And, you know, we were looking at black holes, we were looking at S matrix as the, you know, unique observable according to, you know, how gravity works. And various considerations led us to this picture of like weakly coupled strings in space-time. Although, you know, I really want us to be strongly coupled in the sense of like ask a lot of questions and, you know, you can interact as strongly as you want. It's not gonna ruin this picture. Right. So what is the picture? The picture is we have this worldsheet theory, and we have like the space-time sector, the one that we mostly care about. And I wrote as T because historically it's you know, the Polyakov action, as I said yesterday. But I really want to give credit, you know, to some earlier works of you know, Di Vecchia, Ho, Brink, and other people. I think Desert maybe. So you know, if you have any questions, feel free to ask Paolo. And from this picture, including this internal piece that a priori can be there, there's no reason to exclude it. The space-time description of this worldsheet physics involves supergravity, as I said. And we classified all the options compatible with this gauge redundancy and a good, nice Lorentzian space-time. And we found basically two options, RNS, RNS, and heterotic strings, superstrings, because bosonic strings suck. Because they are unstable in the perturbative description at least. Non-perturbatively, if there is such a thing in bosonic strings, it's complicated. So we were led there. Now, all of this is really hinging on having Weyl invariance. Now, Weyl invariance just comes out of this description, and it's important to even call this sort of abstract conformal field theory thing strings propagating in space-time. To actually assign that meaning to this weird action requires Weyl invariance. Otherwise, it's impossible to go back to the Nambu-Goto description of like, you know, the areas swept by the worldsheet and things that usually textbooks begin from. If you drop Weyl invariance, you can do something called non-critical string theory, which is a whole other kind of worms, and I'm not sure it's actually the way to go. Anyway, we keep Weyl invariance, and this leads us to, well, first of all, to the constraint that this theory, without the coupling to gravity after you gauge fixed, it needs to be a conformal field theory or super conformal field theory. And moreover, it says that the central charges, remember there's the left moving and right moving sector, cannot be just whatever you want, right? Yes. So there's a question that says, choosing the internal theory would be the process of compactifying extra dimensions that people talk about? Or is there no compactifications and therefore no extra dimensions? The answer is both, in the sense that some internal CFTs can be the same as this, but for extra dimensions. You just add more dimensions. And as long as these CFTs are weakly coupled, the central charges will be proportional to the dimensions in the same way as in the RNS and heterotic way. So you just, it's essentially the same thing as changing D up to curvature corrections, which are, yes, I mean, I'll get to that later. So yeah, this is one way to go, just extra dimensions. Another way to go, and you can mix and match if you want. Another way to go is just to have a more abstract CFT. It's just the conclusion is that there must be some other stuff, some other kind of new physics that is not just strings oscillations. So there must be both things, unless you are in the simplest case, which is 10 dimensions. Right. Okay. Good. Good. So yeah. So in this picture, we were led to these conditions. So to this criticality condition, and then to modular invariance, as I will get to eventually. And this gives us this simplest cases. But in general, the quantum mechanical description of these the space-time physics is described similarly to the word line approach for perturbative QFT as this kind of expression. So what do we have here? So remember, it's a 2D supergravity thing, which means that we have our world sheet with some fixed, conditions that tell us we're computing something with some number of external strings, and we sum over the world sheets, right? Now, I want closed strings and oriented strings, which means that the only sum over topologies that I'm allowed to do is a sum over holes or handles. It's a sum over topological invariant called the genus. This little g here. It's a non-negative integer. I just sum over them. And this is the sum over topologies. Now, after I gauge fix the diffeos and the Weyl transformations, generically, I will still be left with something. So there can be a residual thing to worry about, and there can be some parameters in the possible metrics after gauge fixing. Like I can gauge fix to a fiducial metric on the worldsheet, and then its gravitino counterpart as well. But there could be parameters that I cannot gauge fix away, and these are called moduli of the worldsheet description. And so there will be some integral over the moduli space, the space of all such moduli of Riemann surfaces or super Riemann surfaces. And so this is what I'm calling here MG. In general, actually, if I'm acting with if I'm putting some external states, the Riemann surfaces will have little holes called punctures. And so actually you have to change the moduli space a bit. It's not important, but it's in the notes. Yes. I would say it's just an inconsistency of the quantum theory, regardless of supersymmetry. Right. Okay. So, this is essentially the remnant of the coupling to worldsheet gravity or supergravity. And this we won't care too much about except for a couple calculations if I get to them. Then there's the actual integral over the worldsheet degrees of freedom, right? So there will be the space-time sector, the obligatory guys for us, and then possibly other stuff. And then there's the ghosts and super ghosts in the gauge fixed path integral, as you are hopefully by now familiar with. And this is the pretty picture that goes with the equation. Because, why use lot word when few equations and pictures do trick, right? As Kevin from the office said wisely. Okay, so this is the recap. And if there are no further questions, I think we can go ahead and talk about the states. What are states in this theory? How do we describe them? All right. So let's think about states. So in the world line picture, let's just get some intuition from the world line. I can build my Feynman diagrams. I could do everything like that. And the world line theory, it's a 1D QFT, if you will, has some states, has some Hilbert space, has some states. That's great. But can these states actually describe dynamical gravity in space-time? Well, let's think about it. Like, remember the path integral, so the world line path integral contains, I'm not going to write all of it, it's not particularly important for us, has a piece, right, that goes like this. There's the integral over the world line, right? And then there's the obligatory two derivative term. Well, I'm gauge fixing away the world line metric already, but there's the space-time metric, the target space, if you will. And then there's a bunch of other stuff. Now, what would it mean for states to like states scattering in the space-time picture to lead to dynamical gravity actually, like beyond the effective field theory and so on? It would mean that they're able to somehow equivalently be described as perturbations of this metric, right? Like, what if I just take this and I change the metric a little bit? Can I reproduce this deformation within the same theory? That's the question. Like, if I change this g to like g plus delta g, right? What happens? What happens is that I get the same path integral plus, like, the correction to the path integral is the same thing. Like, it will have again this same word line action times a thing linear in delta g, which is just an insertion within whatever correlator of quantity I'm computing of an operator, which is going to be something like this, right? So assuming I can deal with the theory in the background G, I am able to describe the theory in a slightly modified background just by inserting factors of this guy. Right, let me call this V delta G. Right, this is related to something called a vertex operator for reasons that will become hopefully apparent soon. So the idea is, in the world line theory, I can describe perturbations of the background with operator insertions, right? So I have, like, my little Feynman diagram, and then I just add insertions of my V. And this is not just true for the metric, obviously, for any other background field, electromagnetic field or whatever you want, you can just add operators. But operators are not states, right? Operators and states are different things. You cannot just scatter a bunch of gravitons and hope to reproduce this kind of effect. So somehow in the world line picture, which is again perturbative QFT, you can have gravitons, like this has been shown in various works, but somehow these gravitons cannot reproduce this effect of like actually perturbing the metric in some way. Like they seem to be not equivalent descriptions at this level. So enter the worldsheet where something magical happens, right? So this is in the world line picture. Yes.
The capital states driving the world line are not related to its perturbation of the background metric.
Not in this way, at least.
Yeah, that states are not the same.
Yes, exactly. So basically, in this description, you can smash gravitons however you like, but you will not actually curve space-time. This is the pedestrian way of saying it, but yeah. Great. So yeah, what happens in the worldsheet? Worldsheet. Gotta be careful to pronounce the E for long enough time. So in the worldsheet, something very similar happens. Like, you have your, instead of point particles, we have strings. We care about closed strings again. And again, even if you start with open strings, you end up with closed strings anyway, right? So let's say we have this kind of thing. So let me just remark here, we're not adding interactions by hand. Here we have to add singularities in the manifold. Here we don't have to. Interactions are completely fixed. But nevertheless, it would look like something similar happens. Like, the worldsheet action contains something like, I mean, this is the world line, of course. This is the worldsheet. Yes. Like now, suppose we gauge fixed our Euclidean worldsheet metric to something. There's going to be our first Polyakov term.
Sorry, there's a very quick question on Zoom. V delta G is equal to all the integral.
Yes. So this is what's called an integrated vertex operator, right? There is such a thing as the unintegrated thing, which is not just the integrand. It's closely related with some factors of ghosts and super ghosts, right? They are necessary for gauging variance. Well, I mean, I'm not gonna actually explain it. I'm just gonna write it very quickly, but it is in the notes. Good. So, right. So in the worksheet description, we have at least this piece. Then, of course, again, we have a bunch of other stuff. But obviously, there's the MVP or MVM, most valuable metric, space-time metric. So yeah, we have this thing, and we can play the same game. We can vary the thing, and we get a very similar vertex operator. That we get basically an insertion of V delta G. Let's say this is for the word line, and this is for the worksheet. Right? We can just call it like this. Well, okay, I have to write all of it, I guess, because is it even gonna fit? What do you guys think? I'm not gonna write the argument. Yeah, okay. See, it kind of fits. Right. So there is some insertion of this kind. Actually, let me just mention very briefly the correct normalization for these guys that you can find from the unitarity of the S matrix has a factor GS, which is a constant that I will introduce later. This is important for the actual normalization of the scattering amplitudes, but you can find details in the notes. So you get something like this. And I basically, it looks like I'm repeating the same story as before. Like, okay, I can just put vertex operators around the worldsheet, describes a different, like perturbations of a different space-time metric now. So what? It's still the same thing, except it is not, because otherwise, why would I be telling you this? So there is almost, well, I'm not gonna say like words like magical, but it's a very remarkable property of conformal field theories. So the point is that, well, let me write it here. In contrast with the world line case, these guys correspond to states. There's a There's a correspondence between certain operators and states in the theory. In this case, lo and behold, gravitons. So basically what we're saying here is that if we scatter gravitons in string theory, we have to deform the metric. The metric is deformed. And it will turn out to be deformed in a way that at low energies is that of general relativity, right? The dynamics of general relativity plus corrections. Okay, so it's not apparent from here, but hopefully it will be soon. So how does this work? How can operators correspond to states? This kind of makes no sense there's nothing in quantum mechanics that tells us that this should be true. What makes it work is conformal symmetry. So there is a little asterisk here. So they do correspond, but on different spaces, which are conformally equivalent. That's the trick. So the idea is, you have a worksheet like this. Let's say that we play the simplest scenario just for simplicity, right? We have one string propagating like this. Now this is a cylinder, right? This worksheet has the topology of S1 times R, where R is the time direction. Right? Now, what is a state? How do I prepare a state in this path integral picture? Well, a state is basically a wave functional of the fields. You can think like it's a wave functional of the various fields. And basically, you can think of it as a particular type of path integral with some specified boundary conditions in the past, right? Something like this here. And then time evolution takes care of the rest, as you know from standard, everything. Yeah, when some professors say like, oh, well, you know this since kindergarten. Okay, I'm not gonna say that, but it should be standard enough. Now, the thing is that using conformal symmetry, I can map this to the plane, Euclidean space. Like, think about this. Like, you keep this fixed, you open up this part at the end of the cylinder. I mean, it's infinitely long, but bear with me. What happens is that it becomes kind of like an annulus. And if you stretch this in the future and stretch this in the past, it becomes bigger and bigger, and the hole gets smaller and smaller. So in the end, you get, like, for instance, this little slice here is gonna be somewhere here, and time evolution is gonna go in the radial direction, right? And then our infinite path is gonna be in the origin, right? And then everything else is like basically R2, right? So my state preparation in the past becomes some insertion at the origin, which is something local. This is extremely important. So a local specification of the behavior of the fields in a path integral is nothing but an insertion of a local operator. That's what operators do. So there's some operator, some local operator that does the job, right? And you can go backwards. Like there is a one-to-one correspondence of this kind, and it's called the state operator correspondence. Right? This is something that works in CFT. But here in string theory, it buys us so much more because, again, string theory is not just CFT. It's CFT coupled to supergravity. And this is just the perturbative description even. So let's say we accept that there are operators of this kind, and using the gauge redundancy, we can actually show. You can find the details in the say it with me in notes. They have to have some form that kind of looks like this, right? So let me call it V, but then there are some factors of ghosts. Like here we have the B and C ghosts, and these are B, CC bar, let's say. So this is a local operator. And turns out, again, this is a non-trivial thing that holds almost always. Inserting these guys to create states, and therefore computing scattering amplitudes, it's, again, almost always equivalent to inserting the full integrated version, right? So you can basically replace this, because ghosts are annoying, you can replace this with the, let me just write it very schematically like this, okay? So you can equivalently work with unintegrated and integrated vertex operators for most purposes. Good? So now that we have this tool and the physical picture of, hey, states are described by operators of this type, what kind of operators are they? What do they, satisfy? So maybe I can go somewhere else, I guess. So states, we call these vertex operators. Okay. Now, again, this is generally true in CFT, but this is not just CFT. We have some gauge redundancies. Which gauge redundancies? Diffeos and Weil, right? So how are they? How can they be diff invariant and Weil invariant? Well, from this picture, you kind of see already that this is sort of a manifestly diff invariant description, but you also see it from here if you're, brave enough to work with the BRST description of the story. So diff invariance is fine, but I have to say something about it. So before I can tell you what conditions these operators must satisfy to be gauge invariant, I need to tell you how to classify them. And how do you classify states and operators in a theory? According to the symmetry groups. Use the representation theory of the symmetry algebra of the theory, which in this case is conformal symmetry or superconformal symmetry. So we can classify them with conformal symmetry. And so one thing that conformal symmetry bought us is the notion of central charge. Another thing that it bought us is the state operator correspondence. Now there's a third thing, which is the representation theory of the conformal symmetry. What I need here is the notion of conformal weights, right? So the idea is that, conformal symmetry includes like scaling things and scaling locally, in particular in 2 dimensions, because conformal algebra is infinite dimensional. It's called the Virasoro algebra. And moreover, because remember the theory, at least to leading order in the curvatures, it splits in left and right moving sectors. There are scaling conformal weights for the left and the right sector separately. So I can have some little numbers called H. I'm going to say HL and HR. I'm not sure, but I think H stands for holomorphic because in the Euclidean description, you can use complex coordinates, right? You can just say that this is basically C, right? You can use complex coordinates, and then left and right becomes Z bar, holomorphic, anti-holomorphic. I think this is Y, but not sure. Didn't look it up. So point is, there are some numbers here that describe somehow the spectrum in this way. It's not dissimilar from how you do representation theory of the Lorentz algebra, for example. So it's exactly the same. So the question is, what must these weights be in order for our operators and therefore states to be gauge invariant and physical? Well, the Diffeo invariance, having this kind of thing, it tells us that here secretly there's an area element, right? So this thing must be diff invariant and Weil invariant. And if you keep track of how the volume element or the ghosts transform under diff and Weil transformations, you discover that the conformal weights of our V must be equal to 1 in order for our V to describe a gauge invariant physical state. Okay? So this is a thing that we're doing to derive something about the spectrum of the theory. Still pretty abstract, I know. But we can go further because, this is the symmetries. These are the symmetries of the world sheet theory, but we care about the space-time picture. The space-time picture, let's say space-time input. What is the input? The input is that the isometries of space-time are implemented in the worksheet as a global symmetry. And there must be some hint of this in the possible vertex operators. In particular, we know that particle states, single particle states, according to the representation theory of space-time isometries, in asymptotically flat space at least, to leading order in the curvatures, you must have something that you can call momentum, right? There's lots of word, lot of words to just say momentum, right? So there is a quantum number that there must exist, right? These particles can be bosons, fermions, whatever you want. They must have a momentum, notion of momentum. So at least a piece of the vertex operator can actually be determined, can be guessed, and then proven to be the right guess. So this V, it must have a structure. It cannot be whatever you want. So of course you can take superpositions of definite momentum states. It's not, but what about definite momentum states? These guys will have a term. Now, you see that the conjugate variable to momentum is space-time position. So you may guess that it involves the X boson fields, the ones that are always present. And it does. It is this kind of thing. Right? This operator. Of course, there's some normal ordering or radial ordering implicit in the whole story, but just bear with me. And then what else? Well, as I said here, there are some ghosts. In the superstring case, there will be super ghosts. There will be insertions of the super ghosts called that they're called usually beta and gamma, like super ghosts. It's a messy expression. I'm not gonna use it. There can be other things, but what I care about is what sits here. Let me call this V, standard V, not calligraphic V, Latin V, if you will. No, that's stupid. Okay, so let me just call it V. So this V encodes the polarizations. So it could be something like, some epsilon tensor of some, like you can have a definite polarization, dot some V with some indices, right? Because states are linear in the polarizations, remember? So it encodes this kind of thing. Now, in terms of, you see, what we want graviton states to be, you see, the structure should be something like this. So schematically, we would expect, so for example, we could have something like this, to leading order in the curvatures, right? Something like this. So this is true in the bosonic string. In the superstring, you actually have something more like this for heterotics and this for RNS. There are complicated reasons explained in the notes, and there can be other terms, but the point is that the basic structure is there, and we will use this basic structure that gives us polarizations later. Now, notice that up to certain subtleties that I'm skipping, these guys can be symmetric, symmetric traceless gravitons, antisymmetric, and they give us the B field, right? Or scalars, and they give us the dilaton. So these guys are always present in closed weakly coupled string theory. They give us the polarization of our fields, right? So these states correspond to perturbations in those background fields, or if you put in another way, if you put like condensates of these states or coherent states built from these, you can create background fields from other background fields. So in this way, you see that the background is dynamical. It goes with the states. Like everything is basically the same thing. And especially you see that these states are always there. When you have open strings, these guys can go away, but these are always present. When you have non-weakly coupled string theory, this can maybe go away, but this is always there. The graviton is always there, necessarily. There's no escape. Okay? So even if we didn't know about gravity, we will discover it in this way, so to speak. Good. Any questions about this? Yes.
What would it be in the logic? Is it just that's what you can see it, or
Well, so you can make it massive, similarly also the dilaton, if you want. And in some theories, you can even project it out completely, as I said, like in open strings where open weakly coupled strings, it gets projected out. So I don't think it plays a big phenomenological role, although some people are studying it. So if you want to check it out in the literature for like modified gravity theories, it's called the Kalbramond field. Or in the context of superstrings, also Neveu-Schwarz field, NS. Okay, cool. So, right. So we have this piece now. We have some information about parametric operators. What can we say? So now, again, to leading order in the various couplings, basically the conformal weights will split into a sum. And what is the conformal weight of this guy here? So it's non-trivial because it involves this this parameter alpha prime, right? That weighs the curvature, which appears here, right? It appears as a coupling like this, right? This is the string tension. So this alpha prime scale appears in the couplings because curvatures have dimension of, well, curvature, mass squared, which means that the combinations are alpha prime times curvature powers of. So alpha prime is morally the dimensionful coupling of the worldsheet space-time sector, which means that because classically this guy is dimensionless, if it has a conformal weight, it comes to alpha prime orders. So you gotta actually sit down and calculate it. And if you do, it turns out to have h left, h right of this sort of momentum contribution equal to alpha prime p squared over 4. P squared is p mu, obviously. So this is a completely non-trivial thing, at least in my head. I mean, dimensionally, you could guess, but by symmetries and dimensional analysis, it's a power of alpha prime p squared times a constant. But it could have been 0. It's not. So what does this buy us? Well, let's review this condition, right? So let's do it for both for left and right. What do we get? So we get our total conformal weight for either will be something like alpha prime p squared over 4 plus the contribution from the super ghosts plus the contribution, well, I'm omitting some details again, times the contribution from this v, from the straight v, right? And this must be 1. Make sense? This is the physicality condition, if you will. Now, I will discuss this soon, but basically it boils down to 0 or 1/2. Well, actually 1 or 1/2. Let me be more precise. So what I want to do is to flip this around and say that minus alpha prime p over 4, p squared over 4 is hv minus 1 plus this h, right? Why is that? So now I can tell you that this thing will be either minus 1/2 or 0, after I include the various subtleties I didn't discuss. Now, this is the part that we actually care about. It tells us the type of state, right? Gravitons or some other massive states, higher rank tensors, spinors, whatever. This is something related to space-time. You guys can tell me what p squared is, right? So you're probably thinking, it's either plus or minus m squared, depends on the signature, but I never remember, right? Is it just me? Well, in this case, I can tell you it's in the correct signature. It's this. It's the mass squared of the states, like this. Which means that if we turn this around, we get an equation for the mass of these states. So the masses of the physical states are going to be of this type. So this is the thing that I'm going to put in a box. Right? This is the spectrum of physical states, the mass spectrum of single string physical states. So you see what's going on here. Like, apart from this little shift, basically it's controlled by the kind of state. And in conformal field theory, I can just, at least at the free level, I can take these factors and I can put however many I want. I can just put like a bunch of derivatives, x, bunch, I can put a bunch of spinors, derivatives, whatever I want. At least, again, at the free level, then there are corrections. So I can have like powers of states. And the factors and the derivatives will increase the spin and the mass, right? And, for highly excited states, this will be the dominant contribution. What else? The generic value of this guy is just some order one number, which means that the typical scale of these states is controlled by alpha prime, which, so basically this is order of the string scale, right? So this means that string excitations are generically of order of the string scale, obviously. But there can be other scales involved if this thing is itself like alpha prime over some other scale, squared. So there can be other parametrically separated masses, for example, in the presence of extra dimensions. These will be Kaluza-Klein scales, for example. What we care about here is that there is at least a universal power, which is string sized in masses, and it goes on forever. But the gap is at the string scale. Yes.
So you said you can basically have however many derivatives you want with these fields. Then you probably need a parameter to check the dimensions with the masses.
So these are right. So the conformal weight is dimensionless. Okay. It is just dimensionless because it's the exponent by which things scale. Yeah, scale like a power of the Jacobian of the conformal transformation, and that's the power. Yeah. So it counts how many you have, not. Yeah. Yes.
Do the conformal weights correspond to the eigenvalues of the zero modes of the conformal algebra?
Absolutely, yes. In fact, I doubt I will need this later, but yeah, you can basically, from this point of view, if you didn't know about it, you could cook up operators whose eigenvalues are these, and you could call them L0 because L is related to H, and yeah, but you're absolutely right.
Okay, so you do this kind of
Well, what do you mean for the super? I mean, there is a yes, there is a term here that involves them, if that's what you mean. Like the super ghosts have conformal weights. So, I mean, the super conformal algebra has certain generators, right? The L's and the G's, and so maybe that's what you mean. When you gauge the super conformal algebra to do the coupling to supergravity, then super ghosts appear.
yeah.
Okay, that's what you meant. Okay, great. Cool. Good. So, okay. This is pretty cool. Now, are there some leftover questions? I mean, yes, there are, but maybe you can tell me, because I have a couple of questions about this. Oh, okay. So I have a couple of questions. First of all, what are these two options? Where do they come from? Why two options? And second, if you take like the identity operator as conformal weight 0, isn't this negative? Isn't this a tachyon? So there seem to be two open questions here. like tachyon. Like, did you lie to us for 3 hours and a half? And 2 cases. Okay, so where do you want to start? Oh, the tachyon. Okay, so the tachyon. So the thing is, just because you have a bunch of operators that you can construct, doesn't mean that your Hilbert space will contain all of the corresponding states. It seems like it's contradicting what I just said earlier, but the reason it doesn't is that this is a very important thing that perhaps is not emphasized in standard courses. Field theories and quantum systems in general, but in this case in particular. So field theories are basically quantum systems that have to do with space-time degrees of freedom. And we usually care about like local stuff, like these are local operators. But to actually define properly like QFTs, there is global data that needs to be specified, something that cannot possibly be encoded in local things, Lagrangians, operators, correlators, whatever. This is one of those things. So the thing is, my Hilbert space can have a non-trivial projection involved in its construction, such that only a subspace of states survives, right? Now, I haven't been using the canonical formalism here, so I am not really allowed to talk about Hilbert spaces directly like that. I'm using the path integral formalism because it's much cooler. So how can I talk about projections? Well, again, global data. So where does global data show up in the path integral? Shows up in the measure, right? So there's some projection encoded in the path integral measure, in particular in the path integral measure for the worldsheet fermions, which are the guys that I told you yesterday, this is gonna save our asses from the tachyons. So there must be something here. And again, it's not something I can escape from. It's absolutely forced on us by anomaly cancellation and all that. So what is it? Well, I told you yesterday that the anomalies come in basically 3 types: Weil anomalies, diff anomalies of like little diffeos, and anomalies in large diffeos, the ones that I cannot deform away. So the large diffeos, I told you, they lead to the condition of modular invariance on the torus. So the modular invariance on the torus, so when I have my world sheet as a torus, right? Possibly with punctures. What happens is that the anomaly cancellation of diffeos implies that my spectrum must give me some path integral which is invariant under the large diffeos which form this modular group I was talking about. And in order to do this, I must specify what the path integral is. So I must specify this measure. But the measure is not just the local part, which is like Fourier modes of integral over Fourier modes of a discretized torus. There is something else. There is the global boundary conditions of the fermions. So bosons are obviously periodic, right? Like there are 2 independent homology cycles on the torus, right? I often read that they're called the heart and the soul of the torus. I don't know where this comes from, but it's very cool. And so you have to specify the periodicity conditions on both cycles. And bosons are just periodic. There cannot be anything else. But fermions, by spin statistics, are spinors on the torus. So I need to specify if psi both L and right, each has like possibilities like periodic or anti-periodic, right? This is called a specification of the spin structure on the torus, right, which specifies the spinor bundle from which I extract my spinor fields. Right? This is not something I can gloss over. It's absolutely necessary, which means that the actual path integral will be something like a sum over the spin structures of both the left moving and right moving sectors. And then I will have my little, my little integral over the various things. And with this specified spin structures, and then everything else. Right? But my point is that the measure that sums over these things can have some coefficients. Why not? It's part of how the measure is defined. So here is where you see the coefficients that would reject out some states or some other states. For example, from a path integral over the torus, you can compute, a grand canonical partition function of this theory, right? This is completely standard because path integral with a temporal circle, thermal circle, is a thermal partition function. So it's not a surprise. And so these integrals can encode stuff like grand canonical partition functions, and partition functions encode spectra. They are sum over states, right? And therefore, these guys can tell me how the degeneracies of the states are projected, according to this measure. And the choice of measure is not arbitrary. I mean, it's very slightly arbitrary because it must be modular invariant. The result must be modular invariant. Right. For anomaly cancellation, it's needed for unitarity and all of that. Like I cannot escape from this. So there are just a handful of choices, and some of these choices project out the tachyon. So you can just decide if you want to keep weakly coupled string theory as a viable, description. To just choose the ones that kill the tachyon, right? These types of projections are called Gliozzi-Scherk-Olive projections, GSO. Right? There is at least a couple of other ways to understand these projections, but I'll leave it at that, unless you guys have any questions. Was that reasonably clear? I sense a 70% sort of clarity. Could have been worse. But no, but seriously, I'm around for questions whenever. So. Okay. I know it's a lot of stuff to digest, but this stuff is 50 years old. Like, it's a lot of material. Like, not this particular thing, everything. Altogether. Okay, so this is how you get rid of the tachyon. Again, some options will have tachyons, but it's completely fine because like classical backgrounds can be tachyonic, whatever. You can be like at a maximum of a potential or something. The fact that a perturbative description around some background has a tachyon doesn't mean that the theory is inconsistent. It's not a problem. I'm just saying we can choose to discuss the ones that are classically stable just because we care about it. And so we do. Great. And I will tell you what the options are. So we get to choose this GSO projection according to these consistency conditions. But what is the outcome? So at the end of the day, well, maybe I should do this in the, yeah, yes.
Stupid question. So said that you can choose these to project out the tachyons.
Yes.
It must be invariant.
Yes. It is compatible, yes.
Is there any wiggle room?
Or what?
Like if you have tachyons, it's not modular invariant.
Yes.
So it's much more.
No. If it is modular invariant, it may or may not have tachyons. And yeah. Indeed, because the torus is basically you see the little diagram at the top there. It's the one loop 0 point amplitude. It's the vacuum bubble, if you will, in one loop vacuum bubble diagram in the field theory language, right? So it is a one loop effect in the space-time physics sense. So it's a quantum gravity effect, if you will, if you want to put it in this terminology. And we will actually look at this at the very end, because you see, this is this integral here gives us again, the one loop vacuum bubble. And if you're familiar with how one loop effective actions work in field theory, the 0-point piece is just nothing but the vacuum energy density. So basically what I'm saying is that you can compute, well, the one loop contribution. And you could say, okay, this is great, but I can do this in field theory, and then field theory gives me like stuff that is proportional to the cutoff of the EFT to the appropriate power. And that leads to all sorts of hierarchy problems, all kinds of that. This thing in string theory will be much more special. It has very interesting properties. And moreover, here's the kicker. The one loop contribution is calculable and all of that. And then you can tell me, yeah, sure, this is true in field theory, but in field theory, the three-level piece is completely arbitrary, right? In general, the whole vacuum energy in EFT is just a free parameter. It's completely, undetermined. And it would be the same here, except that lambda 3 level in string theory is just plain zero always, period. And this is, again, a consequence of conformal invariance and the Weyl invariance and all of that. If you just compute the answer, it's zero exactly. And this means that the vacuum energy is completely calculable. It's not a free parameter. Again, as I said, there are no free parameters. And moreover, at weak coupling, it will be small because that's what weak coupling means. The loop effects are suppressed. How cool is that? And in a quantum theory of gravity, the vacuum energy density is physical. It gravitates. It does stuff that you can see. So it's important that it be determined, and it is. So I'm going to try to comment about this later. So this is the answer to the tachyon question. Okay? Rabbit holes after rabbit holes. But we got out. But actually, we also got out with something else in our bags. Namely, I told you that you got to specify these boundary conditions, right? And so just for terminology, the periodic ones are called Ramond, R, Ramond. And these ones are called Neveu-Schwarz, NS. Okay? So this is just standard terminology. Or at least, let me be more precise, the periodicity and anti-periodicity that are called R and NS are the ones on the spatial circle on the S1 spatial space. The ones in the temporal circle are just the thermal periodicity. That's something else. But still, you can call them RNS if you want, but you shouldn't. Yeah. So this is the answer now to the two cases. Yes. Yeah, they're exactly the Matsumara modes. Yeah. So now we have, you see, for each left and right moving sector, we have a choice of Ramond and NS. And this is part of the spin structure on the torus in that particular case, but it's completely general. Therefore, I have a bunch of options for my states because the Hilbert space is split in a bunch of pieces. For example, for RNS strings, I have fermions, the space-time worksheet fermions. So the ones that have the mu index, they must be there. They can have these R or NS option for left and right. So 2 by 2, 4. So it's like you have 4 options. Right? Whereas for the heterotic case, you have R and NS on one side, And then other things on the other side. There can be fermions on the other side with other conditions or other sectors from other degrees of freedom. Yes. It's a direct sum. Okay. Orthogonal direct sum. Okay, thanks. So these are sort of the options. What other kinds of sectors arise here depends on the specific thing. Heterotics are kind of weird, but also very cool. And okay, so this is the answer to this, because for both the left and right, so this is true for both the left and the right sectors. You will have to choose, and this will change what is in the vertex operator. Will change the parts that I didn't write, and this will change the conformal weights in a way that makes this 0 for the Ramond guys and 1/2 for the NS guys. Okay. Good. And now with this information, we can actually derive some other things. So where are we at time-wise? It's okay. It's fine.
Equivalent wave moving the tree level, there is a G parity. And the trajectory which are integer G parity plus, not integer G parity minus.
Yes.
And this projection means we do the trajectory G parity.
Precisely. So remember when I said there are at least 2 other ways to understand the GSO projection? This is another way. Absolutely.
That
Well, we have since learned that despite its historical origins, string theory is not a theory of hadrons, directly at least. It's a theory of gravity and other things. Yeah, definitely. I think this is what led, some people to sort of discard it initially for its initial purpose, and then people like Michael Green, John Schwartz were really like, "No, guys, but this has gravity in it. Come on, let's do it." And people didn't care. And then 1984 came along, and then people cared again. Yes. For the dual resonances or yeah.
instead of an intersexual, you have intersexual.
Yeah, it's I mean the whole story started with the amplitudes and the bootstrap thing to describe it. And then these dual resonance models came along. It's a very nice history, yeah, but it's kind of roundabout, I would say. It's interesting. Yeah, okay. So everything more or less clear on this spectrum. The key lessons to remember are that gravitons are always there. In weakly coupled string theory, the dilaton is always there, and this is not an accident, and we'll get to it. And then if there are fermions, at least in the weakly curved regime, you have these decoupled sectors that give you the Ramond and Nemeth-Schwarz sectors. Now it looks like just a bunch of technical jargon, but there is some actual physics in it. So let me tell you what the physics is. So for left movers and right movers, to not confuse this R with the Ramond R, we have at our disposal our psi guys in the Ramond and Nemeth-Schwarz sectors. Now, these are anti-periodic, right? So for example, if you look at the canonical quantization of these guys, you will have some creation and annihilation operators for these guys, right? And you can see this in the vertex operator picture, but it's more complicated. So it's in the notes. So these guys will have oscillators, ladder operators, and these guys will also have ladder operators, right? Ladder operators. This is just canonical quantization of the free limit of the theory. Nothing fancy. But the ladder levels that are allowed from the NS start at 1/2. But in the Ramond case, they start at 0. The reason is that periodic fermions can be just constant. right? It's fine if it's a constant, they can just. So the Fourier expansion of a fermion of a periodic fermion on a circle has a zero mode. It's just a constant, right? So these guys have zero modes in the Fourier decomposition. This is super important because so these are fermion zero modes. Let me call them I don't know, B. Well, these have a mu index, so let me call them like this. Well, it's not that much better, but it's sort of a standard-ish notation, either B or D, you'll find. So why is this important? Because in canonical quantization, these guys satisfy canonical anti-commutation relations, which means that you have something like this, right? So this is the naive writing, of course, but you have the gauge fixing and all of that. It's you can do it. Everything works. The point is that this should remind you of something. What is this? Right. These are the defining relations of a Clifford algebra for the quadratic form of the spacetime magic. OMG, Clifford algebra. What does this mean? This means that because these guys are zero modes, they're not going to change the energy of the vacuum state in the Ramond sector. So the Ramond sector vacuum is actually a non is degenerate. Okay, the Hilbert space of Ramond ground states has dimension more than one, right? How much? Well, dimensions of the of the gamma matrices that you get from this. So it has a dimension, the degenerate. How degenerate? Well, you may recall that these guys lead to the construction of spinor representations in space-time, right? So how degenerate is this vacuum? A space-time spinor worth of degenerate. So this mechanism works exactly the same in the word line. This is nothing to do with string theory. But the point is that this is how worldsheet spinors give us space-time spinors, and therefore fermions by spin statistics, right? So the states that I get by acting with a bunch of stuff on Ramond sector are fermions. Now, this is for either the left or the right moving guys, which means that I get to, I need to do something like this to get fermions, because these are bosons and these are fermions. So these are, well, this. Basically, I get fermions. So this is how superstrings can give you spacetime fermions. They don't have to. There are superstrings without spacetime fermions, but these always have tachyons. It's proven now. So in order not to have tachyons, I must have these guys. So string theory predicts fermions, I guess. And gravity, pretty cool. Right, and then you have, so these are the RNS and NSR sectors, right? So these guys in the superstring, and then for heterotic theories, we will also have something similar. These are spacetime fermions, and then we can have like NS and NS. Sorry, R. And these are bosons in spacetime. So everything, acting on whatever. And again, for the heterotic, you only have one of these, and then you have something else on the other side. Yeah. So the point is that there are both bosons and fermions, and this is how you distinguish them. This is why it was important, right? Like it looked like technical jargon, useless, crap, but it ain't. This is useful for actual spacetime physics we care about. Okay. Any questions?
they have to get an electron in string case.
By electron, you mean the precise thing with the precise mass and everything? No. No. But there's a property of the electron that is always true in string theory. So let's say consider massive particles with an abelian charge. Let's say that the space-time physics has a U1 gauge redundancy, electrodynamics sort of, and you have charged particles, right? Then the electron has a neat property that in Planck units, it's lighter than its charge. So basically, if you put two electrons like this, the gravitational attraction is overcome by the Coulomb repulsion, right? And in string spectra with such a U1 gauge redundancy, there always is such a state, always a self-repulsive state. So in this very, very loose sense, one of the key properties of the electron, which is relevant for quantum gravity, actually, it is always satisfied. But other than that, I don't know. What could I not get? Sorry. Sure, but this is kinematics though. Like I cannot. The precise mass of the electron needs a very precise construction of everything else. But the qualitative features of the electron are absolutely there. Yeah, that's not a problem. Yes. So it's the vacuum, a vacuum, of the world sheet theory. Therefore, it's a single string state from the space-time viewpoint. Okay. So in the world line picture and also worksheet, the idea is that you're dealing with single particle states, and then they interact in space-time, and you can put as many as you want, right? So this is a single particle state. So the thing is that, you know, because strings can oscillate, basically, like here, like a point particle can basically just have like a momentum and some internal, degrees of freedom. A string has a center of mass momentum, and like it can also oscillate and have an internal degree of freedom. So these are the kind of Hilbert space we're talking about. Like the minimal oscillation is the ground state. Cool. All right. Good. So now we have a bunch of states, and now I can finally get to this arrow. So I can tell you, you see, we have some states, let's say for simplicity, that there is no conspiracy of scales in such a way that all of these states are weighed by the string mass. There is no other separate scale. This is false when there are large extra dimensions, for example, but let's forget about it. The simplest case is this. So I have a bunch of states, and some of them will be massless, and everything else is string scale with like towers. So it makes sense to distinguish them like this. So the massless states will give me the low energy physics, and then everything else is responsible for the high energy stuff, with eventual backlash and feedback, let's say, on the low energy part. Okay. So before moving to that, I would just like to tell you a little bit about the string landscape, but there's not a lot to say. Maybe I can erase this. All right, so these are sort of general features of the spectrum, right? But as is apparent from this formula, the details of the spectrum depend on the precise weights that you can have, right? And the precise vertex operators too, like what kind of polarizations and degeneracies you can have. So these details are encoded in the vacua because everything else is built on that. So they're encoded in the superconformal field theory, essentially. The precise spectrum of states you can have. And so there's a notion of like this landscape of vacua that you can have, right? String landscape. The reason for this is that, you see, like, again, in this corner that we're talking about, a worldsheet theory determines a vacuum of the space-time theory. I guess space-time. Well, let me just call it vacuum again with all the caveats that I talked about yesterday of the quantum gravity theory in space-time and the spectrum around it, and their interactions are fixed. Therefore, also whatever low energy EFT describes the low energy physics around it is completely determined as well. So here's the notion of landscape, right? The set of these constructions is the set of like EFTs that you can have. Right? So the idea is that because of the consistency conditions that are extremely stringent, basically what you get is that within the pool of available EFTs, you get only like a negligible subset of options. For example, like the typical garden variety QFT that you may use for some purpose can have multiple continuous parameters that you can change. This is a huge infinity of theories, in fact, of EFTs. Whereas here, you don't get to change anything, right? Everything is completely determined with some very strong consistency conditions, and there are no free parameters. So what you end up with usually is that the distinct EFTs are like, you know, the little grapes in a panettone, right? So that's the notion of a string landscape. Like everything else is not part of the string landscape. It's in the string swampland, if you will. But yes, so this is the idea. Now, of course, I cannot possibly give you a rundown of 20, 30 years of finding classes of EFTs in the landscape, but I can give you the simplest example. Simplest examples. What are the simplest examples? But by now you should be able to tell me 10 dimensions. Because in 10 dimensions, I basically have no internal part of the worldsheet theory, which means that everything is spelled out by the GSO. That's the only degree of choice, right? Again, for closed strings, open strings are other, they give you other things to worry about, like orientifold projections, if you want to look them up. Yep. So if you do this, what do you end up with? You end up with, in closed weakly coupled string theory, you end up with 5 theories that have no tachyons. Yeah. So the options are, well, there are 2 of the RNS type, RNS, again, this is the proper wording, and 3 heterotic. So these are called the type 2A theory, the type 2B theory. These are the ones. At the closed string level, you have also so-called type 0A and type 0B, but they only have bosons, therefore they have tachyons, right? So discard them for these lectures. Then there are 3 heterotic theories. Now, heterotic theories are weird because, like, again, all the interesting stuff appears in the other sector that can be a lot of things. But it turns out in 10D, the GSO is so strong that it tells you what it must be. And they must be some degrees of freedom that give you, in the space-time picture, they give you Young-Mills fields. They give you gauge groups, right? So the low energy theory is not just gravity, dilaton, blah. It contains Young-Mills as well, which you can also get in RNS strings, but you have to use things called D-branes. It's a whole other kind of worms. So basically, I'm telling you this because the nomenclature for heterotic theories is based on the gauge group that they have, right? So here there are basically three options for the gauge algebra that you can have, and we sort of know what the gauge group is. But let's say I stick to the gauge algebra for now. You get a gauge algebra which is SO32, and because this is an orthogonal gauge algebra, we just call it HO. Then there is an E8 plus E8 gauge algebra, which doesn't mean that the gauge group is E8 times E8. It could be like a quotient or a semi-direct product. It's complicated. Therefore, we call it the exceptional heterotic. And then there's a third option, which has an algebra of SO16 plus SO16. And people just call it the SO16 plus SO16. There's no better name for it since 1986. Okay, so these are the five guys that are not tachyonic at the purely closed string level. If you include open strings, there are other types like the type 1 theory and the type 0 prime B theory and the USP32 theory. There are other options. And then there are other options further with tachyons in 10D, but not a lot of options all in all. Order 10, I would say. No, these are string perturbative limits that with the full high energy description included. And of course, they also have their respective effective field theories. In particular, here they reduce to what are called type 2 supergravities, of which there are these two types. And why type 2? Because there are two supercharges worth of supersymmetry in 10 dimensions, which is the highest amount you can have for an EFT of gravity. Right? So these they reduce to these, and these they reduce to these guys also have space-time supersymmetry, like these guys. Again, I told you these are the simplest ones. And these they reduce to something called type 1 or heterotic supergravity plus super Young-Mills because they have gauge groups, and type 1 because they have one supercharge, not two. And these ones has no SUSY, right? And therefore, the low energy theory is just some EFT coupled to Young-Mills and dilatons, like some EFT. Yes, I extensively studied these EFT like in some papers, and you can just look it up if you want, but like it's not SUSY, it must have some problem. Yes. So it's not an inconsistency, at least not as far as we are aware. The issue with actually dealing with it is that because there's a dilaton always. So in this theory, there is a scalar potential. So here the scalar potential is forbidden, it's 0. Here there is a scalar potential that looks like e to the 5/2 phi. So it's a runaway potential that has no minimum or something like that. So it's kind of difficult to deal with the runaway. And that's all there is to it. Well, I mean, there's my whole PhD that there is to say about it, but yeah. Yes. Well, the perturbatively these are connected by something called P-duality, and this also, which is a perturbative gauge redundancy of string theory, if you will, which you can see perturbatively, but you cannot see in the effective field theory. It is a string effect. In field theory, T-duality does not exist. Like phenomenology. Yeah.
Start from one single of these field
Yes.
and then all into low energy.
Yeah.
And the low energy will be different.
So yeah. Yes, but yeah, but there's another option, right? Another option is to reduce to lower dimension by either, well, by compactifying or by replacing with some other internal CFT. Compactification is sort of special, not just because it's more intuitive, but because it's more directly connected to this physics. Like if you compactify on something big, you can work with the 10-dimensional EFT and reduce that. That doesn't usually work super well, unless you have SUSY, of course. Or you can compactify on something stringy, so that there never is a 10-dimensional EFT. You only have the 4D EFT, and there's a gap to the rest of the degrees of freedom. This option is very much underexplored, but I do have a paper which has been ready for like 2 years, maybe even 3 years, and we have not published yet. But basically, it's a strategy, it's an alternative strategy to do Fino in order to get a 4D description without SUSY, which doesn't secretly have like huge extra dimensions that you should see. Like the extra dimensions are tiny in this scenario. So yeah.
Quite possible at least you see any field that is like a X field.
I would say no, naively. I think to actually get something close to it, you have to work harder than this. This is just the simplest case. But there are some papers by Steve Abel and collaborators who show, thanks to like the general properties and constraints of this worldsheet CFT business, that if you have something like that, then it must have some very cool properties. Like there's a connection between the dark energy, vacuum energy density, and the Higgs mass. Like there are some non-trivial constraints between the various CFT quantities. So if we get something like that, then, but it's hard to get something like the Higgs. Yeah. When I say it's hard to get something like the Higgs, I mean something that lives in the fundamental of some, electroweak-like gauge group, because something in the unjoint is much easier to get.
So if you find like, sorry for the, if you find a weakly coupled string theory, which is not long, is like here.
Yeah, there's many more.
X field, at least some field that would look like X field, then that would be a more, let's say, promising option to start and then going to the low energy.
I think so too. Yeah.
But it's still not clear.
I would say no. I mean, maybe I'm missing something, but I would say no so far. It's like the broad strokes are there in the sense that non-abelian gauge groups are there. Gravity is there. Scalar fields can be there. Like the various chiral fermions can be there. Anomalies, Kants, and all that. So the ingredients are there. Like dark energy can be small. Like all the pieces of the puzzle are there, and so, like it's hard to get all of them to fit together. This is part of the problem of any quantum gravity construction must contain everything at the same time. You don't get to just ignore pieces. Right. So if you want to be strict about it and not just do toy models, either you get everything right or you don't do it. So that's kind of the problem. But this is not the problem of string theory, of course. It's about everything.
That like the standard, the field content that we have, but not the right, like the right Wilson coefficients that describe the standard model or the passive.
I mean, possibly, I guess I cannot exclude that option at the moment.
Yeah, I mean, you cannot, you didn't get it so far, or you didn't.
Right. No, but no, I would say no. Yeah. Cool. All right. Good. I mean, okay, maybe I can just close with some little comments. No, I think yeah, I think we can move on to the coffee break, I guess. Yeah. But yeah. Okay.